When looking at the polygonal masonry of Peru, many people doubt that such precise fitting could have been achieved by working with stone in its solid state. This task seems too challenging. It's clear that achieving such results would have been much easier if the stone were in a softened state, utilizing the property of liquids to fill the space they are given. This idea is supported by the appearance of many blocks, their facades and the details on them. Indentations on their surfaces sometimes look like the result of pressing into softened material. All this provides grounds for speculation about the plastic states of stone, their possible degrees, and the methods for achieving such states. Let me clarify immediately. I am setting aside the fact that large-scale production of geopolymers requires significant industrial capabilities. This is because not every type of stone can be obtained from natural materials, such as volcanic ash or lime. Moreover, the stone must be of various types and high quality. Let me emphasize that the compressive strength of ordinary concrete is up to 5 times lower than that of granite and several times lower than that of microcrystalline limestone. And this refers to industrial concrete, with granite gravel as aggregate. The strength of pure cement mortar without aggregate would be even lower. The reason for the high strength of natural stone lies in its formation process under high pressure, and in some cases, high temperatures. Therefore, producing concrete of comparable quality requires industrial equipment. Simply pouring a primitive mixture without vibration, pressing, or proper aggregate will result in short-lived blocks. The very fact that these walls have stood for hundreds of years is undeniable proof of natural stone. Chemical analyses are not required to determine the natural origin of the stone. It is enough to use a sclerometer to test the hardness of the blocks. Wherever this has been done, the results show values unattainable for artificial mixtures, especially primitive ones. Let's also set aside the fact that multiple analyses confirm the material is natural stone. And the question remains, why cast entire blocks from concrete if masonry with mortar could be used, as we do today? It would be possible to create masonry similar to dry stone construction, incorporating joint separation to allow for slight movement of blocks, achieving the same effects. Reasons for such an approach could be imagined, but no rational explanation exists. We will focus solely on the stone state, specifically, its presumed plasticity. 2 distinct approaches can be identified. The creation of artificial stone, including geopolymers, which may be based on volcanic ash or lime for limestone. The manipulation of natural stone, which undergoes some form of treatment to alter its structure on the surface or to a certain depth. The search for such treatments has been ongoing for a long time. For example, it has been suggested that pyrite could be used to create acid, or the sap of an unknown plant. There's even an exotic hypothesis involving irradiation creep, among others. Once again, we will set aside the mechanisms of these effects. Let's divide the possibilities of working with softened stone into categories and discuss each one individually. This can be schematically represented as follows. Softened natural stone. Geopolymer stone. By the term geopolymer, I will refer to all types of mixtures used to create artificial stone, regardless of the binding agent. These can further be categorized by viscosity into flowable, stiff, and a separate category for dry packing. In this case, the mixture is in powder form and lacks fluidity. A common example, given for this approach, is cement bags that have compacted over time. Let's start with geopolymers. First, we must consider that the blocks contain many natural veins of other minerals, which would have to be imitated. Let's leave this aside for now, as well as the question of why, instead of making standard blocks, they chose to create ones of various sizes. Let's examine what doesn't align with the use of a liquid material. A liquid geopolymer would inevitably seep into gaps. Flexible formwork could be used to prevent this, fabric, polyethylene, or other materials. But this would not stop the overflow of one block onto another. Additionally, the pressure exerted by a liquid mixture can tear through inch-thick boards, let alone weaker materials. Liquid mixtures also shrink as they solidify, which, in large volumes, could lead to cracking. Without the use of vibration, voids would remain. And applying pure slurry, without aggregate such as gravel or stones, is a pointless solution. This would significantly reduce the strength and result in unjustified labor costs. There is no gravel in the blocks. This is evident from the fractures. Nor are there the inevitable prints on concrete, left by not only the builders but also animals, which, as we know, love to leave their marks at construction sites. It's also difficult to explain the bedding joints on the blocks. If these were the result of depressions, there would be deformation at the edges. Since there's no deformation, the next row must have been cast atop already hardened blocks. But then, where did the indentations come from? Were they deliberately made on hardened concrete? That would mean working with a weakly solidified material. Straight joint lines also require explanation. When pouring into molds, the result would be bulging, uneven lines, which would then need to be leveled. But again, this would involve working with solid material. The back sides of the blocks also need explanation. These often resemble rough natural stone. Any type of formwork would inevitably smooth the shape, and rounded forms like these cannot be achieved by simply backfilling with soil. When a block contacts a rock face, controlling the backside of the block becomes practically impossible. The absence of layering is another question. Each block has a characteristic texture and color, which would require preparing the exact amount of mixture for each block, avoiding the formation of layer separations. How would rectangular blocks be created? Flexible formwork wouldn't work for this. If the shape were ensured by casting an entire row at once, with the sides compensating for the pressure, the result would still be arch joints, not straight ones. Forming joints that intersect multiple blocks without additional processing becomes even more complicated. But this processing would only be possible after initial setting. All of this combined suggests that a liquid consistency cannot be applied to the creation of polygonal masonry. Let's move on to high viscosity consistency. Many of the contradictions with the liquid state remain unresolved. It would still be impossible to eliminate overflows. This will be discussed in detail below. Layers with varying colors for each portion of the mixture would still remain. The issues of creating the back sides, the absence of aggregate, and the seating areas persist. And where do the gaps between masonry rows come from? Was the back of the formwork intentionally coated to form gaps, which are sometimes significant? To all of this, we must add the process of creating bedding joints in the rocks. Were these also cast from concrete? Did they imitate cracks and veins, only to later carve out the block seating in the hardened material? Once again, this would involve working with solid material. It's important to note that creating bedding joints for the next block in the masonry or rock is essentially the same process as removing material to form stone configurations. These configurations are often located on limestone outcrops, which exhibit characteristic traces of chemical erosion, parallel grooves in a vertical direction, following the movement of water. This process is caused by acid rain, including volcanic in origin, which fell during the rock formation. Malham Cove is an example of such an eroded limestone formation. The erosion processes occurred in solid rock. For this reason, stone configurations cannot be classified as places where liquid material was extracted for construction, or as quarries where solid limestone was mined. In many cases, only small amounts of stone are extracted. Instead, this process involves the deliberate creation of a set of planes. The smooth profiles of the joints also remain unexplained. Why would they be needed if the blocks could simply be cast? Irregular forms would actually improve cohesion. When using dry packing in flexible molds, it's possible to shape the sides and prepare the upper row to the desired form, as well as adjust the backside. This is achievable because such a method maintains its shape and behaves more like a solid body than a liquid, retaining its form. This demonstrates that the closer the material's state is to a solid, the easier it becomes to achieve the desired shape for the blocks. However, with dry packing, it becomes very challenging to imitate cracks or veins of other rock types. Overlaps between blocks would still occur. Knobs would become entirely unnecessary, as there would be no place for them in the sequence of work. Furthermore, at all discussed viscosity levels, bevels would not be required. These could be explained as the result of joint marks if no molds were used. However, without molds, voids would inevitably be filled both underneath and to the sides. With molds, joint finishing wouldn't even be necessary. Additionally, when clearing joints in an unset material, inevitable tool marks in the form of scratches, aligned with the movement direction, would appear. There are no such marks, neither on the edges nor on the blocks themselves. Quarries are also difficult to explain. For example, in the Kachikata quarry, which supplied granite for the Temple of the Sun in Ollantaytambo, megaliths with traces of processing remain to this day. These traces match those found on the blocks. This raises questions. Were the megaliths cast first, then processed, and only afterward transported to the site? The existence of inset blocks is also puzzling. Why cast small, separate blocks when they could have been made as part of the main structure? And why cast inserts between the blocks and the rock when a block of the required size could simply be formed right away? Moreover, these inserts always have a wedge shape, which allows them to be installed in a solid state. Additionally, the natural stratification on the blocks is evident and is often positioned at an angle. This suggests that during their fabrication, the blocks were specifically cast at an angle. How exactly was this done, and how was such uniform stratification achieved? As we can see, the use of artificial stone faces numerous inconsistencies, ones that are fundamentally irresolvable. These inconsistencies diminish as the material's state approaches a solid, but retains the possibility of effortless processing. Let us now turn to the alternative, the use of natural stone that has undergone a change in its state. In this case, all the natural characteristics of the stone remain intact: its composition, defects, and veins. The issue of creating bedding joints in the rocks is also resolved, as the same treatment applied to the blocks would simplify the processing of the rocks as well. How should bedding joints be created if they were formed in a softened state after the block was placed? In such a case, the edges would inevitably be deformed. If the material was solidified, this would again involve working with a hard state. Once the seating areas are prepared, the block is installed. But how can one avoid filling the interblock space? If the lower portion is not softened, tight fitting cannot be achieved. If the lower part is extremely stiff and highly viscous, achieving tight joints would require significant pressure. This creates an unsolvable paradox. The denser the material, the greater the pressure needed to create a joint. But the greater the pressure, the more the material penetrates into voids, leading to bulging. These are interconnected processes. Even flexible formwork would not help in this situation, as it would be pushed out of place. Only rigid formwork could work, but rigid formwork has thickness, and it's unclear how it could be removed afterward. Most importantly, what's the purpose? The penetration of the material into voids would only enhance the bond. Within a single block, one of the voids may be omitted, while another features a locking protrusion, a special element for fixing the block. This protrusion often does not align perfectly between the lower blocks. Since there are no bulges between blocks, nor any penetration into joint spaces, it means there was no plasticity in any form, neither throughout the block's volume, nor in a thin layer of it. A thin softened layer wouldn't be sufficient to achieve full jointing. However, any irregularities would inevitably imprint on adjacent blocks. At any depth of processing, the surfaces would have to be pre-shaped for relatively precise fitting. It is impossible to take rough stones and simply join them together. Precise joints would either not exist, or would be irregularly curved. However, preliminary shaping means working with solid material. Furthermore, there would be instances of incomplete jointing sections, where the surfaces failed to connect properly, since it would be impossible to visually control the contact process. Such inconsistencies are absent. The joint surfaces, as mentioned in Part 1, change in appearance as they move away from the front face. This effect would be impossible to achieve through casting, as the texture would remain uniform. This suggests surface treatment, becoming increasingly precise toward the edge. A separate possibility is a mixed approach, where some blocks are natural, with veins, and others are cast from geopolymers. This approach does not solve the problem. For the natural hard blocks, it would still be necessary to create jointing profiles, which again involves working with a hard state. There are no examples of rough surface joints, even though such joints would enhance the masonry if geopolymers were used. The unfinished sections of masonry are also telling, where blocks stand without lateral joints. It is clearly visible that the lateral sides were later leveled to match the next block. When casting, both the lateral and top sides would need to be formed at once. There are several studies attempting to substantiate the use of geopolymers. One of them is the article, Tiahuanaco monuments in Bolivia are made of geopolymer artificial stones, created 1400 years ago. The key arguments for the artificial origin of andesite are as follows. The first is that the quarry for obtaining andesite blocks has not been studied. Therefore, it is impossible to compare samples from the blocks with those of natural stones. However, the quarry in the slope of the Cerro Capilla volcano is publicly accessible, and the tool marks on the blocks match the traces found in the Cachicata quarry in Peru. The second argument is that traces of organic matter were discovered in the andesite, which is supposedly impossible for volcanic rocks. It is proposed that the andesite was created using volcanic tuff and guano. This argument is also incorrect, as there is extensive research on the presence of organic matter in volcanic products. Entire research institutions have worked on this topic, as there was a hypothesis that life could have originated through volcanic heat as an energy source, and an ample supply of basic components. Thus, andesite containing organic matter could have formed naturally from volcanic activity. Regarding the assumptions about the artificial origin of sandstone slabs, the varying heights of the slabs suggest that they were produced separately. Casting blocks with angled sides and then joining them together is pointless. The fact that the slab consists of separate blocks is indicated not only by their height, but also by the damage inflicted in modern times, whereas the marks of the plates being fastened together are ancient, made during the construction of the platform. Furthermore, the slabs bear distinct marks of processing. Another study by Andrei Varianov. In 2012, at the request of the Peruvian Ministry of Culture, a ground-penetrating radar survey of Sacsayhuaman was conducted due to the threat of further destruction of the complex. The research was carried out by a Russian team, which also collected samples for analysis. Even at the sample collection stage, methodological errors became apparent. The limestone material taken from the blocks was dense and lacked visible organic remains, such as shells, whereas the single sample taken from the so-called quarry, or rather from a nearby limestone outcrop, had a different structure. However, to properly establish a match between the stone used in the blocks and that of the quarry, multiple samples should have been taken from limestone outcrops with the most similar structure. The analysis determined that the stone of the blocks is microcrystalline limestone, with minimal or no organic remains. Moreover, the composition and structure of the block material matched a sample from a limestone outcrop located within the complex itself. The so-called quarry stone was identified as organogenic limestone, leading to the conclusion that the limestone blocks were artificially produced. However, this actually suggests either that the quarry is located elsewhere, or that the sample was taken from a different geological layer. Another argument made by Andrei Varianov and Alexei I in favor of the artificial origin of the blocks is their claim that such a microcrystalline structure could form only under specific, and therefore artificial, conditions. This argument is weak. Microcrystalline limestone, also known as micrite, is a widespread natural rock. Studies exist on samples of the same structure and composition. Further evidence of an incorrect conclusion is the fact that the same block samples were analyzed in another laboratory, and the results confirmed their natural origin. Thus, the question of microcrystalline structure is purely geological. At present, no convincing arguments support the use of geopolymers, neither at the sample level nor at the logical level. The latter is actually the decisive factor, as geological knowledge is still incomplete, and the complexity of replicating fully identical conditions prevents direct experimental verification. So how were the blocks and rock formations processed on such a massive scale? Despite the mystery and complexity of the question, there are only a few possible answers. I do not subscribe to any particular theory, as this would compromise objectivity and hinder research. My task is to present the facts. The first is the use of enormous labor efforts and processing with simple methods. This argument is valid. Individual aspects of the masonry can certainly be reproduced. However, common objections remain. Why such efforts were necessary, how such precision was achieved, and why so many unfinished areas remain. Then, a hypothesis emerges about a certain factor that facilitated the processing. There are only two possibilities. Either the stone's strength was reduced, softening, melting, or an unknown method of weakening the rock, or incredibly advanced tools were used that ignored the rock's hardness. There are no other options. Thus, either the stone was processed with conventional tools, advanced tools were used, or the rock itself was altered. If it were a case of advanced tools, we would expect to find extensive tool marks. Yes, some marks do exist, and they will be discussed in a separate video. However, in Peru, they are extremely rare and do not resemble high-tech manufacturing methods. In fact, they contradict such an idea. Additionally, these marks are found only on exposed rock surfaces, never on the blocks themselves. This is a significant argument. There are no high-tech tool marks on thousands of blocks. The only remaining possibility is modifying the rock itself, something akin to softening, but not making it plastic, just weakening it enough for easy shaping with simple tools, whether copper chisels or stone implements. For example, water is used in both the manual processing of soft limestone and the industrial scale cutting of hard stone. It facilitates the process and protects the tools. Additionally, forming an abrasive paste based on water or oil significantly eases the cutting process. Other methods also exist. For instance, hydrogen embrittlement can weaken structural integrity. The idea of material weakening also raises my skepticism. However, it has almost no inconsistencies, except for one, the exact mechanism of the process, which could be quite simple. At first glance, the unfinished sarcophagus in the Cairo Museum does not seem unusual. Indeed, granite can be processed using hard abrasives and copper tools. Let's focus on the striations that appear directly in the cut zone but are absent above it. In experimental core samples, the opposite is observed. Striations are less pronounced at the contact zone, due to abrasive fragmentation, and instead form above the cut zone, where the paste with larger grains is pushed out. This fact has been documented in research conducted by those advocating for direct processing with copper and abrasives. It is important to remember that what needs to be reproduced is not just the final result, but also the processing marks that directly indicate the methods used. After all, the same result can be achieved in many different ways. And on the sarcophagus, the situation is the opposite of what occurs in experiments. Scratches are distinct in the cut zone and then disappear. It is logical to assume that they were erased by the movement of the cutting blade itself, which is strange, since soft copper cannot polish granite through its own motion. There is another factor, the widening of the cut as it deepens, and it is extreme, as is the incredible depth of the cut itself. This is how one would cut soft limestone, but not granite. And if such cutting was performed, then the capability existed and was effective. As a result, we see signs of primitive manual tool use. Manual, because the direction of the cut changes and the widening of the cut suggests the tool was not fixed. Yet, the cut itself has peculiar characteristics. This also explains why the analysis of Sacsayhuaman blocks revealed copper particles. The stone allowed for processing with simple tools. It is telling that, in this case, all traces of stoneworking generally align with the technological level of the local culture. The marks on the edges of the blocks and rocks become clear. They resemble layered removal of material. Such traces could only be intentionally made using simple methods. If the material had been in a plastic state, there would be scratches, as mentioned earlier. Here, however, there is a distinct trace of layer removal from a solid surface, similar to a planer mark on a wooden board. At the same time, the widespread stone processing is also explained. If the methods allowed for it, why not establish mass production of stone vessels, especially if it was even easier than working with clay? Again, I do not claim to have a definitive answer. However, I must point out that in the weakening hypothesis, the factor was external. At some point, it disappeared, leaving behind unfinished projects. Additionally, cultural inertia must be considered. Stoneworking and the creation of artistic and utilitarian objects would have continued by tradition, with gradual improvements in techniques and tools. Each proposed theory has its shortcomings, and the correct one will be the one that accounts for all physical and logical evidence. For example, the widening of the cut could be explained by sawing in a horizontal plane, instead of a vertical one. The expansion of the cut occurred due to the outflow of abrasive material, simultaneously polishing the surface and removing scratches. Although this approach seems impractical and requires additional effort. Leave your thoughts in the comments. Thank you for watching and for your support. See you next time.